So we're gonna review for the midterm. I'm gonna present first the major topics that you really need to know for the test. You need to know how to calculate the area between two given graphs. Like you're supposed to graph the functions, maybe two quadratic functions or a cubic and absolute value, or it depends on the functions. But you need to know how to set up the integral and integrate that. And to recall what that is, to find the area, so let's call this topic 1. To find the area, it's always going to be the integral from a to b, the upper or top graph minus the lower, top, lower, or bottom, dx. Or it could be the formula, the integral from c to d, the right graph minus the left, after you draw the rectangle, dy. So no matter what kind of area question they ask us, this is exactly going to work the same for all of them. Volumes. Volumes using washer and shell methods. In washer, how do we deal with washer, or how do we use washer? Let's call part A washer method. Washer method is the volume formula is pi, the integral from a to b, f of x squared minus g squared of x dx. And this f of x, that's called capital R, or the outer radius. And this is the inner radius. So let's say you are revolving the thing around this axis. You draw the rectangle must be perpendicular to the axis of revolution. Notice the triangle has 2 points. So what you do is the capital R is the distance from the furthest point from the axis of revolution, which is this, and the smaller r is this. So outer radius, inner radius. Same thing works with dy. It's going to be f squared of y minus g squared of y dy. For shell, the volume would be 2 pi integral from a to b, 3 things. The average radius, the height of the rectangle, and the thickness. This is just a formula. So the thickness, as you know, is going to be either dx or dy. Now, remember, in the first one, here the rectangle must be perpendicular to the axis of revolution. Here the rectangle must be parallel. Arc length. I'm not going in order by the section. I'm just going by just topics. Arc length. So the arc length has a formula. What's the formula? The integral a to b, the square root of 1 plus the derivative of the function squared. Don't forget derivative and don't forget the square. Dx. That's the arc length. So usually, just to remind you, you on the side, if there's a question on this, you find what that is. You find its square on the side. Don't do the work under the radical. It's easy to do the work on the side. And then you find 1 plus f prime of x squared on the side. And then whatever you get, you place it under the square root. It's easier this way. 4, we are gonna talk about the integrals. So you are responsible for all kinds of integrals. So almost every question you're gonna come across has things about integrals. Now the question is, how do we approach an integral? So if you see an integral, it asks you to integrate it. How am I going to approach solving integrals? Right? So the first thing we do is I look at what kind of methods we learned or kinds of integrals we learned. So you have to have those all kinds of integral in your head and say, okay, let me try this. Doesn't work. Let me try this. It's a process of elimination. So the first thing we know is the u sub. If it doesn't work, that's the easiest. You try u sub. If it doesn't work, you try by parts, integration by parts. If not, it could be trig integrals. If it doesn't work, trig substitution. We have other kinds of integrals. We have partial fraction decomposition, right? Partial fractions. We have the improper integrals. So u sub is the easiest. That's why I try it first. I look at it. Does it work with u sub? Oh, it doesn't work because it takes 5 seconds to check. If not, you want to look at by parts. Usually by parts, if you have something like x squared, let's say sine x, or like ex cosine x, or x, like usually a function with another function, or ln of x over x squared, or something like that. Trig integrals, when they give you trig, in like there's sine cube cosine to the 4th, let's say, or tangent to the 6th, secant to the 5th. Trig sub, usually, so this one's usually like there is sine to the 5th x cosine to the 4th. That's an example. Trig sub is when you have like usually square roots, like let's say 1 minus x squared, for example. Partial fractions, that's when you see fractions, maybe like x over x squared minus 4 dx, let's say, but no, let's multiply it by x plus 1. Impropers, mostly when you see what? You see negative infinity on the bound, like this, f of x dx, or positive infinity, let's say a to positive infinity f of x dx, or where it is not continuous or something, but focus on the infinities. When you do improper integrals, we'll show you an example. It's important to follow the steps, not just randomly write your own way. Next one is surface areas. When you have a positive function that has continuous derivatives, we define the surface area of the surface obtained by revolving or rotating the graph y equals f of x over the interval from a to b about the x-axis is given by s equals the integral from a to b 2 pi times y square root of 1 plus f prime of x squared dx. Now if we do it about the y-axis, what we get s equals the integral, say a to b 2 pi x square root of 1 plus f prime of x square dx. Next is the centroid or center of mass. Centroid or center of mass. How to find, if we give you a region bounded by graphs, how do I find the centroid of that? Right? So if you have, let's say you have like this and the line, so you want to find the centroid somewhere there. That point, centroid, we call it x bar, y bar. We need to find x bar and y bar. So how do we do that? To find x bar, we first need to find what we call m, which is defined as rho the integral from a to b f of x minus g of x dx. That's small m. And then mx, m sub x, is rho the integral from a to b x times f of x minus g of x dx. And my is rho times the integral from a to b 1/2 f square of x minus g square of x dx. So after these we can find x bar, which is my over m, and y bar mx over m. The comparison theorem. The comparison theorem said if you have two functions g and f that are continuous with f of x bigger than g of x, bigger than or equal to 0, for x bigger than or equal to a, then there are two things. If the integral from a to infinity of fx dx converges like it has a value, then the smaller one has to converge. A to infinity g of x dx converges. B, if the integral from a to infinity of g of x dx diverges, then the integral from a to infinity, the bigger one, that forces the bigger one to diverge as well. we will look at some examples how to work things out here. Eight, orthogonal trajectory. So usually you are given like a function, say like y equals, for example, kx squared or something. They want you to find the trajectory, the orthogonal trajectory of the family of the curves, where k here is any constant. The way things work is, first you're going to differentiate both sides with respect to x. So you get like dy dx equals 2kx. And then from that one, also, you want to solve for k and substitute it in there. And after you find dy dx, orthogonal means perpendicular. So to find the equation for the orthogonal, you do opposite reciprocal of whatever you get. Then find the opposite reciprocal. And from there, you can continue solving. You can integrate and simplify or solve. Also, solving differential equations. And here we have two things, either separable or linear. Separable, you're going to separate the x's together, the y's together, integrate and solve. The linear, you have to do more work. You have to look for p of x, q of x, find the integrating factor, multiply both sides by that I of x, and then solve it from there. One more thing is the average value of a function. Average value of a function talks about of a continuous function over, let's say, the interval AB, we calculate as f average is 1 over b minus a integral a to b f of x dx. So first example, it's section 6.1. I'm going to do number 14. The problem talks about sketch the region enclosed by the graphs of y equals x squared and y equals 4x minus x squared, and find the area. First thing we need to do is to graph it. That's the y equals x squared. If I want to graph the next one, I can take x0, y0, x1, y is 3, x2, y4. If you set y0, x would be 4. So it seems it's coming down this way, about a rough sketch. And that's the region bounded by the two graphs. Now we draw a rectangle. That tells me it's dx. As well as I need to know where the two graphs intersect. So to find their intersection, we set them equal to each other. Add x squared to both sides, divide by 2, and factor. So that tells me they intersect at 2 and 1. So this is 2 at 0. So then the area is going to be the integral from 0 to 2. The upper curve, which is 4x minus x squared, minus the lower curve, x squared, all that dx. And it's very easy, straightforward integration. No need for u sub, no need for any other method. Next question from section 6.2 about volumes. So basically find the volume of the solid obtained by rotating the region bounded by the graphs of y equals 6 minus x squared and y equals 2 about the x-axis. Make sure you sketch the graph. So first we always need to sketch the figure. X0, y6. If y0, x plus or minus square root of 6. And then y equals 2. This is y equals 2. So the region I'm revolving is this one. And we are revolving this about the x-axis. So the easier way is to have a rectangle perpendicular to the axis of revolution, like so. So that tells me dx. Perpendicular means I'm using washer method. So in washer we have this as capital R and this as small r. So then the volume in this case, pi integral, we need to see where do they intersect. So we set them equal to each other. Negative x squared is 2 minus 6, negative 4. X is plus or minus 2. So it's from negative 2 to 2. We do the first one square, which is the function itself, the 6 minus x squared, minus the 2 squared. And then it's easy to integrate something like this. Now we look at a problem from section 6.3. Section 6.3. Number 20. Number 20. So the same thing, find the volume of the solid obtained by rotating the region bounded by the graphs of x equals 2y squared and x equals y squared plus 1 about y equals negative 2. So first we're going to find where do they intersect, and then we're going to graph them. So to see where they intersect, we set them equal to each other. The x equals x, subtract y squared, so y would be plus or minus 1. Okay. So if I want to sketch the graph for this, let's sketch it here. The first one, x equals 2y squared, when x 0, y 0. When x is, let's say, 2, y is plus or minus 1. So it's going to go like this. That's the first one. The other one, when x cannot be 0, when y 0, x is 1. And then what happens is, if you take x2, y would be plus or minus 1. So when x is 2, y would be plus or minus 1. And if you want to know how this is going to be traced, you can substitute x2 also in here. So that will give you 2 equals 2y squared. So again, you get plus or minus 1. So they both going to intersect at the same point here. And if you take 3, x3, y for the first one would be 3/2 y squared. So y is plus or minus root 3 over 2. For the other one, if x is 3, see, it's going to be bigger. So the green curve is going to go past the other curve like that. This is the x equals y squared plus 1. And that's where the region that they form together. And we're going to rotate this. Remember, they intersected at y equals 1 and negative 1. So what I can do, I can erase all this stuff, because I'm going to draw the axis of revolution, which is y equals negative 2. That's the axis of revolution. If we do a vertical rectangle, it will be very difficult to solve. So only horizontal rectangle can work here. So when I'm talking about horizontal rectangle, I'm talking about a rectangle parallel to the axis of revolution, right? Parallel. So first, that tells me is going to be dy. It's going to tell me dy. The other thing is it's shell method. So shell method is going to be used. So in shell method, the volume is 2 pi. Don't forget the 2 pi. The horizontal rectangle can move up and down from negative 1 to 1. Negative 1 to 1. And we need 3 things. The thickness is dy. I'm done with the thickness. I want to find the average radius. If you remember, the average radius is the distance of that rectangle to the axis of revolution. So what do we have for the average radius? So I'm going to write here so you know what that is, average radius. Again, average radius is the distance from the axis of revolution to the rectangle. So now people say, okay, what am I going to draw? I drew the rectangle somewhere there. Some people maybe might draw it up here. Someone might draw it down there. It doesn't matter where you draw it. What happens, we think about it as the distance from, if I draw it on the top, that's a y distance, right? That's a y distance. Plus, you're going to go all the way down, that's a 2-unit distance. So it's going to be y plus 2. Or you can say y minus negative 2. Then we need the length of the rectangle. the length of the rectangle, we do the right minus the left. The right graph is y squared plus 1 minus the left graph is 2y squared. Notice how the region is symmetric about the y-axis. So when you evaluate things out, you can make it 4 pi from 0 to 1, y plus 2, 1 minus y squared dy. So you double it and go from 0 to 1 instead of negative 1 to 1 by symmetry. And then you can multiply all of this, distribute and integrate and do the work. And I remember, I think the answer was 16 pi over 3. Section 6.5, number 10. They said, let f of x equals 1 over x from 1 to 3. This is a very simple function. Find the average value of f over the interval 1 to 3. Over the interval 1 to 3. Then find c if f average equal f of c. So to find the f average, we recall the formula area 1 over b minus a is 1, b 3, integral from a to b, the function itself dx. So that becomes 1/2. The integral of this is straightforward, natural log of x from 1 to 3. 1/2 natural log of 3 minus natural log of 1. Natural log of 1 is 0, so we get this as an answer. Then they said find c if f average is f of c. Well, we just found f average, natural log of 3 over 2. F of c is 1 over c. Then you flip both sides. 2 over ln of 3 is c. Okay, next, on page 508, that's the section where they have miscellaneous integral problems. We're going to do number 50, the integral of 1 over x squared, square root of 4x plus 1 dx. Or wait, or let me do not this one. Wait, sorry. Let's do the integral number 72. 72 is the integral of natural log of x plus 1 over x squared dx. So we use integration by parts. We take the u to be the natural log. So from here, du is the derivative of that over itself, dx. And what is left is dv. So dv is dx over x squared, which can be rewritten like so. So v is the integral of that, or negative 1 over x. So then the integral is uv, so that's negative 1 over x times natural log minus the integral of v du, so it becomes plus, and du is 1 over x plus 1. So that's what we got. And then what we need to do here is, for the second integral, we need to do integration by partial fraction decomposition. The good thing about this is very simple to work with. A over, so 1 over x times x plus 1 is a over x plus b over x plus 1. And I'm sure everyone can solve for a. A would be 1, b would be negative 1. So then the integral becomes 1 over x minus 1 over x plus 1 dx. Negative 1 over x, ln of x plus 1 plus natural log of the absolute value of x minus natural log of the absolute value of x plus 1, and don't forget the plus c. You can leave it like this, it's fine. Just a good note, while you're working with integrals, do not forget the dx. We see a lot of people forget to do the dx. Another one is number 51. So 51 is the integral. That's the one I wanted to do, not the other one. X square root of 4x squared plus 1 dx. So for this one, that looks like trig substitution, because by parts doesn't work, u sub doesn't work, partial fraction doesn't work. So here what we need to do is look at the stuff under the radical that can be rewritten as 2x squared and 1 squared. So in this case, 2x is 1 tangent theta. And you remember the map for the work, we have three things. We differentiate both sides, 2 dx, derivative of tangent is secant squared theta d theta. So this means dx is 1/2 secant squared theta d theta. Also, we need to find the quantity under the square root, tangent squared theta plus 1, which is secant squared. And this comes outside as secant. And the last one is to solve for tan theta, which is 2x over 1. And that helps us to construct the right triangle. Tangent is opposite over adjacent. By the Pythagorean theorem, we get 4x squared plus 1. Then the integral becomes, on the top you put 1/2 secant squared theta d theta, and in the denominator we have, first, if you look outside, we have x, and x is theta over 1/2, so 1/2 tan theta, and also the square root came out to secant theta. Notice how the 1/2 cancel and the secant cancel, and that will give us secant theta over tan theta d theta. So if I want to integrate this, u sub doesn't work. Maybe I want to convert it into sine and cosine. So 1 over cosine theta over sine over cosine. So the cosines cancel. That will be 1 over sine theta d theta, which is cosecant theta. Now, before we proved and gave you a formula for secant theta. You can do the same thing for cosecant, which is going to be natural log of opposite value of cosecant theta minus cotan theta plus c. So then this is natural log. If we go back to the triangle, cosecant, we know it's the reciprocal of sine, hypotenuse over the opposite. So the hypotenuse was the square root of this over the opposite, which is 2x, minus cotan would be 1 over 2x plus c. You can combine inside the opposite value or leave it as is. Both are fine. Section 7.8, number 20, it says integrate 2 to infinity y e to the negative 3y dy. You can tell that's an improper integral. So what important about improper integrals is you need to rewrite this first, say 2 to a, limit as a goes to infinity of y e to the negative 3y dy. And then on the side, what I do, I always take that y e to the negative 3y, try to integrate it without the bounds. It's much easier. And one way to do this is u sub. So we can take u to be the y, du is dy, and dv is whatever is left. So v is negative 1/3 e negative 3y, because if you have e integral of e to the a y dy, it's 1 over a dy. Now we write this integrator on the side, uv minus the integral of v du dy. So that gives us negative 1/3 y e negative 3y minus 1/9 e negative 3y. So that whole answer goes in here. From 2 to a. And we can finish it down there. So here we can get limit as a goes to infinity. Substitute the a first, so you have two things. So negative 1/3 a e negative 3a minus 1/9 e negative 3a. Substitute the 2 in, negative 2/3 e negative 6 e negative 6. Now, when you pass the limit, this one here, this goes to 0 because e negative infinity is 0. But this one, it's a problem because that's going to go infinity times 0, indeterminate. So what we can do, we can use L'Hopital's rule for that part. On the limit, a, bring that down like that. So this goes the limit as a goes to infinity, derivative to the top a, derivative to the bottom 3a, 3a. So 3e to the 3a. The bottom goes to infinity, so that goes to 0. Now that confirms that this also goes to 0. So the only thing left is multiply the negative on the last one, 1/9, and combine them. If you combine them, you get 7 over 9 e negative 6. So the integral converges. It has a value, it converges. Same section, number 50. 50, they said use the comparison theorem. Use comparison theorem to determine if this integral converges or not, or diverges. So this is the integral. So when we try to use the comparison theorem, one thing about the comparison theorem is, you know, x bigger than 1, right? So we know that sine x in general is between negative 1 and 1. It goes up and down. But sine square is between 0 and 1, right? 0 and 1. So this means the top equation, the 1 plus sine square x, that's going to be bigger than or equal to 1. Like, so this quantity, when I have the sine square, this will make this quantity bigger than or equal 1 over square root of x. Right? So then what happened is, if you integrate both sides, from 1 to infinity, then what I'm going to do, I'm going to look at the right hand side, this one. I'm going to do that one first. So we can integrate that on the side by bringing it up as -1/2. So it becomes 1/2 over 1/2, or 2. So 2 square root of x. So now when we do the 1 to infinity, we do limit as a goes to infinity, 1 to a, same thing. But we already integrated that as 2 square root of x from 1 to a. Then limit as a goes to infinity, 2 square root of a minus 2. And this gives us infinity. So that tells us, note that that integral diverges. That's what infinity means. If that diverges and the left hand side bigger, then the given integral also diverges by the comparison theorem. Same section, number 52. Integral 0 to infinity arctangent of x over 2 plus e to the x dx. About this, what's difficult the most is to find the other function that you need to integrate. But arctangent, if you want to just recall how the graph looks like, it goes like this. There's a horizontal asymptote here, another horizontal asymptote. This is pi over 2, negative pi over 2 asymptotes. So, but notice the integral starts at 0. So from 0 on, notice how arctangent, so you can say for x bigger than or equals 0, arctan of x is always less than pi over 2. See, I'm trying to create an inequality somehow. Right? Now that pi over 2, if you like, and it's fine, you can make it, that's like 1 point something. You can say it's less than 2 if you want. If you want to clean up the pi over 2. But doesn't mean you cannot continue with pi over 2. It's fine. So let's say I'm doing this. Then I'm going to divide both sides by 2 plus ex. Now the one on the right side maybe is difficult to integrate. Then you can say the larger the denominator, the smaller the fraction. So you can rewrite it like that. It's less than this. Why did I do this? Because now when I integrate both sides over 2 plus ex dx from 0 to infinity, it's less than the integral of 2e negative x dx from 0 to infinity. Now the left-hand side, everyone should be able to integrate that. The right-hand side is, if you integrate it on the side, e negative x dx, that would be negative 2e negative x. And if you pass the limit and do the work for all of this, and then you pass the limit as a goes to infinity, this will give us an answer of 2. So the left hand side is smaller than the right hand side. The right hand side goes to 2, converges to 2. So that forces the left hand side, like the left hand side, which is the given integral, to also converge to also converges by the comparison test, comparison theorem. Section 9.5, number 20. It says solve the differential equation x squared plus 1 dy dx plus 3x times y minus 1 equals to 0, provided y of 0 is 2. Here you can tell this is y prime, and divide everything by x squared plus 1. Then we need to distribute this 3x over x squared plus 1 y minus 3x over x squared plus 1, which you can move it to the other side or add it to the other side and get 3x over x squared plus 1. This is a linear differential equation. It's not separable. So to do that, we know p of x from this is 3x over x squared plus 1, and q of x is the one on the right side, 3x over x squared plus 1. Then what we need to do is to find the integrating factor. I, or I of x, is e the integral of p of x dx. E integral of 3x over x squared plus 1 dx. And the top one can be integrated using the u sub. U sub u is x squared plus 1. That will give us e integral of 3/2. So it's going to be, if you integrate that, it's going to be 3/2 ln of x squared plus 1. So move that 3/2 up like so, and then e ln of anything is the thing itself. So that becomes x squared plus 1 to the 3/2. We multiply both sides of the equation by the integrating factor, and we always have to get I of x here times y, all derivative, equals q of x, which is 3x over x squared plus 1 to the first power, times the integrating factor. So then on the left side it stays the same, as you can see. This stays the same for now. The right hand side there's a 1, so 3/2 minus 1 is 1/2. So integrating both sides, that will drop the derivative here, and then we need to integrate this one. Don't forget the dx. Now, how do we integrate the right hand side? We use the u sub. Again, u is x squared plus 1, du is 2x dx. So you need a 2 and 1/2. So 2 inside, 1/2 out, so that gives me 3/2 integral of u to the 1/2 du. So keep this the same. 3/2 u to the 3/2 times 2/3 plus c. Then the left hand side stays the same. U to the 3/2, now we can replace it with x squared plus 1 to the 3/2 plus c. Now if you divide both sides by x squared plus 1 to the 3/2, That'll give me 1 plus c over this, which you can rewrite it as 1 plus c times x squared plus 1 to the negative 3 halves. This is called the general solution to that differential equation. Notice they give us a condition y of 0 equals 2. So this will basically telling us to find what we call the particular solution. So you substitute x 0, 0 squared plus 1 to the negative 3 halves, and the y 2. So that tells us 1 plus, that's a 1c. So c is 1. So when you find c1, you substitute it back into the boxed answer to get 1 plus x squared plus 1 to the negative 3 halves. This is called particular solution. Other problems you can do on page in the textbook 538, number 20, from section 9.3, you can do 8, 18, 20, 30, from section 9.5, number 14, practice is the way to go. And you should probably like summarize all the formulas, come up with a formula sheet that summarizes all the formulas, the tricks for your reference. You can refer back to it last minute. You can work on that, you know, like, oh, let me review them before I get to class. Another thing, like when you walk into the test, if there's a formula that you always forget, you can, like, as soon as you take the test and there's nothing in your desk, maybe you write it down somewhere if in case you need it, you know, you can use it, right? Like we've seen students in Math 3A on the final, what they do as soon as they walk in on the back side of the test, they write all the integral formula before they start reading any question, because they know they're going to use them. And then as soon as they start the test, they start flipping back and forth back to the formulas.